Excuse me. Thank you, Dr. Vijit, for your warm introduction. I thank Center for Data Science, Siksha Anusandhan, for inviting me to deliver, give a lecture in the weekly academic lecture series. So today, I'm going to talk about parametric curves and their parameterization. I hope I'm audible. Okay. Okay. So Uh, this topic actually is uh, undergraduate topic, generally taught or should be taught uh, in the vector calculus portion. And when I was a student, I never happened to learn this thing. So I came to know about this thing in my MSc. So that was too late, sort of, to learn. And then also the topic reappeared in my PhD courses. Later, when I got opportunity to teach vector calculus in our institute, I relooked everything and saw, the kind of thing I should have learned, and which I should deliver to the students so that I could learn. So it's a quite a recent thing. I mean, this I learned very recently. Recently means maybe 5 or 6 or 7 years. The thing is that, so whatever I'm going to deliver cannot be got in a single book. Okay, it is multiple books. Through multiple books, if one goes, then only one can get it. Okay, so this I have tried to squeeze in one lecture, and I hope I'll be able to finish within 1 hour. So this is my plan of lecture. First, I will start with parametric curves, its definition, examples, then reparameterization of parametric curves, then negatively oriented parametric curves, following arc length and arc length functions, and need to have a correct parameterization, and that would be arc length parameterization. So that's the plan. Yeah, so let's start. So first we define parametric curve. So in any function which is continuous, defined on an interval to R3 or R2, or in general Rn, Euclidean space Rn, is called parametric curve. So that means if you are thinking the curve is in R3, then for any t where t is coming from the interval, it would look like xt, yt, zt, a point inside R3. So if you take all the points, that means the image of gamma, which is gamma I, that will define the curve. So all the points on the space that constitutes the curve is that gamma I. And in that case, gamma is called parameterization of the curve. So note that here it is said a parameterization. That means maybe many parameterizations will be there. So that will be seen. Here this curly bracket gamma, we call it trace of gamma. So it means the curve C, which is denoted gamma I, along with one ordering, and this ordering happens to be coming naturally from the interval I. So interval I is a part of real line, and in real line you have a natural ordering. So that natural ordering can be viewed to be inside this curve. So let me talk about it. So let me switch to the whiteboard. And so suppose we have here in the interval, suppose AB. So I is the interval AB, and the curve I'm drawing is suppose gamma t. So any point t is here, and correspondingly gamma t we are getting. So this point suppose this point suppose your gamma A, and suppose this point is gamma B. And in the real line, the orientation is this orientation. So like first A, then intermediate points, then B. Accordingly, here also we get an orientation. This is the ordering of the points. So it is like if 2 points are there, T1 and T2, so where T1 is less than T2, accordingly, I'll be getting the points on the curve. So for T1, the first point I'll be getting is gamma T1. Because T1 is coming first, since you are tracing as if the gamma T1 curve first appears, then it appears gamma T2. So automatically our ordering comes, and this ordering let us denote by this symbol. So this is a natural ordering on the curve coming from the interval, and that ordering we call to be an orientation. Now it is very much well known that whenever you talk about any parametric curve, that means you are actually talking about curve with an orientation. And then you see there can be two types of orientation. One is that you are moving the points like from here to that side. So arrows are defining the orientation. Another possibility is this side. So it is like same curve in the opposite direction. We'll come to that one later. Okay. So let us first talk about parametric curve, which is coming with an automatic orientation. Let us not reverse it for the time being. The interesting thing is that even if it is not a parametric curve, any curve can be given an orientation, and that is by 3 points. So let me talk about that. So it is like, so suppose you have a curve. So this is a curve, suppose C, and it is not a parametric curve. We have not defined any parameterization for it. Then if you have the curve is such that the 2 points, this n 2 points are not same. So that means it is not a loop or a closed curve. Then this, if you define the first point, suppose this is the point, let us say P1 point, and this is P2, then this P1 comma P2 will define an orientation. It means first P1, then intermediate points, then P2. However, when the curve is a loop like this, where the end point and beginning points are same, then 2 points on it, suppose this 2 point I'm saying here it is P1 and here it is P2, is not enough to define the orientation. It is because from P1 to P2 you can reach two ways. One is this, another is this. So this P1 comma P2 does not give ordering on it, which is not ambiguous. It becomes ambiguous. So you need another point. So if I say P1, P2, and P3, sorry, P3, then this P1, comma P2, comma P3 on the curve defines ordering. It is like first P1, so the arrow from P1 to P2 is like this, then P3. So P1, P2, P3 defines an ordering. If you want to have reverse ordering, then you say the ordering P1, then P3, then P2. Okay. So not necessarily just parametric curves having orientation. The orientation can be given in any curve. So if the interval is closed interval AB, then the first point gamma A is called initial point, and the last point gamma B is called final point of gamma. Now, if initial point and final points are same, then it is called loop or a closed curve. Now, a closed curve will be called simple if the function gamma is 1 to 1. That means there is no self-crossing in the interval A, B, where the B is not there. I mean, A closed A, open B. So it would look like this. So if I take a circle, then it is a simple one. Or this curve is simple. Whereas the figure 8, if I draw, then it is not simple. It is because in the, so suppose this one has been traced in 0, 1. So suppose gamma is the curve from 0, 1 to R3, which gives you this. Then if you check the curve in the interval 0, close 0, open 1, then it is not 1, 1. Look at when we are talking about this curve, is this circle. Suppose the circle I'm parameterizing as cos t, sin t, where t is running in between 0 to 2 pi. So this is an example of parametric curve where this circle is your x square plus y square is equal to 1. So all these points on R2 which satisfies this relation x square plus y square is equal to 1, then gamma t would be the parametric representation of this circle. Now, if you draw the axis, then this point will be 1, 0, and you can see gamma of 0 is equal to gamma of 2 pi is the point 1, 0. However, if you look at the function gamma on the interval 0, 1, then it is 1, 1, whereas previously the gamma was not 1, 1 because at 0, sorry, not 1, it is 2 pi. At 0 and at 2 pi, it has one value, single value. But if you remove that one, then the function becomes 1, 1. So it starts like this, and it is a non-ending curve sort of. Okay, so it will look like, so here the picture will look like, it will start from this point and it will not end. It will keep going and going and going. Okay, so here it is clearly is 1, 1 function gamma. This one cannot be. Okay, so whenever we talk about non-simple curve, it is curve where it has self-intersection. Now let us take example. This I already have told you, that suppose we are in R3 and the curve is x square plus y square is equal to 1 circle at the height z is equal to 5. Okay, so in the plane z is equal to 5, we have the curve x square plus y square is equal to 1. Then the parameterization would be cos t sin t comma 5, where t is running between 0 to 2 pi. Now the same curve gamma t, so same curve is represented by both gamma t as well as this delta t, where delta t is cos 2 pi t sin 2 pi t 5 comma 5, where t is running between 0 to 1. So it is very much clear that a single curve can have more than one parameterization. So the automatically question comes in that how many parameterization is possible for a given parameterized curve. So we'll come to that one. Now about the figure 8, so this is the figure 8. This is a non-simple parametric loop. You can check very easily, and it is very evident from the equation 2. And the parametric form is a sin t cos t, when t is running between 0 to 2 pi. So one can very easily check this is not 1, 1. In 0, close 0, open 2 pi. Now, some remarks about these parametric curves. First, we should understand that whenever we have a function, any continuous function on an open any interval AB to R, then as if the interval got weighted. So any points on the interval carries a weight fx. So it looked like this. So you have an interval AB and you have curve fx here. Then as if each of the point on this interval having is given, so this is point x in the interval, is given a weight x. So you need not think this is a curve for the time being. So curve means I am talking about x fx, and whenever I'm thinking about curve, this AB as a curve, then I'm thinking about this x point as x comma 0. Okay. So it is like previously it was interval which represented the line part of x-axis, x comma 0, where the point look like x comma 0. And whenever the interval has been given a weightage such that each point x is given weight fx, then it bends the the straight line. Okay, so that means whenever I'm saying something is parametric curve, then it is actually interval which has been given a weightage, or a straight line which has been given a weightage. And in that case, fx is weight. Okay, so automatically, whenever this question, whenever I say this, automatically this question comes. So since AB, interval AB has been given weight, so interval AB can be viewed as a straight line segment, and it has length b minus a. So does it mean the length of b minus, so length of the interval b minus a is same as the length of the curve which is generated by that function f? That means this length of the curve x fx, where x is running between a to b. So for that one, what you have to do, we have to learn how to measure the length. So that I'll be coming to. Okay, and in general, we'll be seeing that's not true. Length of the interval need not be length of the curve. But around this question, lots of things are there to learn. So I'll be discussing this thing in detail. So if I say that this interval is weighted by f, so for the function f, you are thinking an interval AB is weighted, and then what is the meaning of the integration a to b fx dx? For sure, if you translate along that line, it will be weighted length of the interval AB, and which you know as the area of the area under the curve x fx. So area under the curve x fx is the integration a to b fx dx, is same as, you can think this is a weighted length of the interval AB, or weighted length of the line segment which is starting from a0 and ending at b0. Another question comes in, does it mean the integration a to b fx dx is length of the curve C? Answer is no. You can check very easily that if you triangle, so this right angle triangle will look like something like this. So so this is your x-axis, this is 0 0. Then you get a right angle triangle with correct length, both AA. Okay, so you check, you can find A such that the length of the curve, the length of the curve is A and A to A, is not same as the area of the curve, area under the curve. This one can check very easily. Okay. And this I already told that whenever I say gamma is a parametric curve, then automatically, as the first case I described, it can be seen as the interval AB, or the corresponding line segment, has been weighted by a vector. So gamma x is a vector, or is a point. Okay, we say as a vector. So then what is parametric curve? Parametric curve is nothing but weighted line segment or weighted interval. Now we're coming to the case that how many parameterization is possible to a given curve. So let us start with this example. Circle has been parameterized as cos t sin t, where t is running between 0 to 2 pi. Another parameterization is cos 2 pi t sin 2 pi t, where t is running between 0 and 1. So they represent the same curve. Set up all points xy such that x square plus y square is equal to 1. Now I'll be showing that there are infinitely many parameterization to the same curve. So how the thinking goes on. So suppose the curve is C and gamma is the given parameterization. So you can think this first case that gamma is cos t sin t. Then I'll be talking about the process to get this new parameterization delta t. So the process is the following. First, you transfer the interval AB. Transform the interval AB to another interval CD, so that you get a function theta which sends the interval CD to AB. Then theta is a function. You compose that with gamma. So you have gamma compose theta, that would be a function from CD to the curve C. Note that the points on the gamma, that means the curve C, or if you say gamma I, those does not change. Why? It is the following. So let me go to the board and draw it. So it is the following. So this is your interval AB, and this is your curve gamma. So any point is going to gamma t, point gamma t. And what is the curve C? C is all these gamma t. T is running in between A to B. And your plan is to get another interval C to D such that this CT is completely transforms into AB, such a way the orientation of the interval does not change. That means any point here goes to any point here in between. So in between A and B, C goes to A, D goes to B. If it happens so, if this is your T, so some point here, call it to be S, will be going to T. So as S goes to T, essentially it will be going to gamma T. So S actually is going to, so if this function is theta, then S is going to the same gamma T via gamma compose theta. So gamma compose theta S is nothing but the point gamma T. So the points on the gamma does not change. Only what happens, the interval changes. Interval of the gamma. And
what, Professor? Excuse me. What about the orientation? Will it change or not?
it will be same because C is going to A, B is going to B, and accordingly all other points. So I'll be coming to that one. Okay, I'll coming to that one.
Okay.
So that's the plan. That you generate a function theta where interval CD will be going to interval AB, and then rest will be taken care of by the given function gamma, such that the orientation is preserved. So this we have to ensure. How it is ensured that 0 is going to A, 1 is going to B, and intermediate points also will go accordingly. Then, so the question I put, what happens otherwise? Otherwise means if the orientation is not preserved. So that I'll be discussing later. So at first I'll be focusing on not disturbing the orientation. Next is, if the gamma is simple, then it should be preserved. If it is not simple, then also it should be preserved. That means the theta should be very nice. In that case, it should be 1, 1. If it is 1, 1, then only the property of gamma in terms of the simpleness is preserved. Next, gamma is automatically a continuous function. So to preserve the continuity of gamma, you should have continuity in theta. So theta has to be continuous. Next is that if gamma is little bit nicer curve, if it is C1 type or C2 type, or in general Cn type. So meaning of Cn type is it is n times differentiable, and after differentiation, whatever the function you get is continuous. So we simply say it is continuously differentiable n many times. So in that case, if gamma is Cn type, then the Cn-ness of gamma should be preserved. So in that case, the theta has to be Cn type, because we know that if two functions are Cn type, their composition is also Cn type. Continuous of composition of two continuous function is continuous. Composition of two C1 type function or differentiable function is differentiable. Twice differentiable function is also twice differentiable, and accordingly it goes on. So here we need theta Cn type if gamma is given to be Cn type. So what is the main idea? Main idea is the geometry of gamma. Whenever I say gamma, it is actually about the curve. So geometry of the curve should not be disturbed by the parameterization. We should not choose parameterization so that the curve changes its geometry. So this 1, 2, 3, 4 points will make sure that that is not going to happen. Sorry. So note that this 1 and 2 together will tell you first it is onto and it is strictly increasing. Okay, it's strictly increasing. It increases from C to D to B, the interval A to B. Now I'm talking about some examples. So the thing is that do you have any example which is such kind of nice? Answer is yes. Any linear function, if you take any linear function, means fx is equal to ax plus b. So fx is equal to ax plus b, if you take, you know it is infinitely many times differentiable. So it is Cn type function. This continuous. It is 1, 1, strictly increasing. So it satisfies all the property. So the question is, can you have such kind of function? Answer is yes. So we'll divide into two parts. First is we'll be converting the interval to 0, 1. So I'll be finding a function from 0, 1 to AB. Then next step. So from 0, 1 to AB, if you want to get a function which transforms the interval 0, 1 onto the interval AB, the answer is very nice. So it is coming from much more general discussion. It is that you have 2 points, P1 and P2. So in any Euclidean space, suppose you are in R2. In that case, what would be the line joining these 2 points? The parametric equation of the line. So then it would look like, the parametric equation would look like lambda times the last point P2 plus 1 minus lambda to the first point P1. Sorry, P1. So note that I'm saying here, so I'm giving a name, it is theta lambda. So lambda times last point. So when I'm saying it is last, that means I should get it last point. And 1 minus lambda times P1, the first point. Then one can check very easily, this theta of 0 is P1 and theta of 1 is P2. And that exactly has been done here. Here, the last point is B, first point is A. So S, I'm thinking about the parameter. So B times S plus A times 1 minus S. And then the function, which I have given a name psi AB, transform the interval 0, 1 to AB. Clearly, this is a linear function. So it satisfies all the properties which I demanded earlier. And hence, the new parameterization would be any curved gamma on the interval AB. You compose that curve gamma with this psi AB. Then the psi changes its domain to 0, 1. And the new curve or new parameterization will be gamma compose psi. So this is the first step. Second step is, suppose we have the curve delta, whose domain is 0, 1. And I want to change this domain 0, 1 to any domain CD. That means my plan is to get a function phi which transforms the interval CD to 0, 1, satisfying those 4 properties. Then we are done. Now here also answer is very simple if you take linear functions. So the way I described here also the similar thing can be done. So assume this T is running between C to D and you try to change to interval 0, 1. So the process look like this. So you should have T running between C to D. You convert this interval to 0, 1. So you subtract C. So it is T minus C less than D minus C. And then D minus C, since it is non-zero, divided by. So you divide T minus C by D minus C. And actually the interval got transformed into 0, 1. That's all. So, so the function here in that case would be t minus d divided by d minus c. This function transforms the interval CD to 0, 1, and it satisfies all the properties we demanded there. And hence the new parameterization of delta would be delta compose phi. Now with these two functions, psi and phi, we can change any interval to any interval and reparameterize curve. So how that would be done? Here the process. So we have psi, we have phi, and the curve initially you take from AB to C. My aim is to change the interval to CD, get a function theta, and I will be sticking to linear function. In that case, my plan is convert the interval to 0, 1. So introduce function phi, sorry, not psi. Psi converts the interval 0, 1 to AB, and then phi converts CD to 0, 1. So then gamma compose psi compose phi, I can take it as theta. So that would be a new parameterization. Now you count that how many parameterization is possible, because the interval AB I can convert to any interval CD. So this any interval are infinitely many. It may be 0, 1, it may be 0 half, it may be 0 third, it may be 0 1/n, or it may be anything, any proper interval. In that case, I'll be getting infinitely many compositions which will be giving the same curve. So given any curve which is parametric, it has infinitely many parameterization. And you can take the previous example. So if we have the curve, this cos theta sin theta 5 circle on the plane z is equal to 5, and it has a reparameterization, then one can check this gamma is nothing but this delta. For delta, the parameter interval is 0, 1. So in that case, gamma can be written as delta compose phi 0, 2. So what it does, it transforms the interval 0 to 2, 1, and then through delta, it gives you the same curve gamma, same parameters in gamma. So that's how gamma and delta are parameterization of same curve, different parameterization. Now one can check this, the way we have formed this psi and phi, they are inverse to each other. Means if you compose psi with phi, it will be identity, and phi with psi again, it will be identity. So that's why you can get delta also from gamma. Okay. Yeah. So this is I have written here that phi compose psi, if you take the interval to be AD, it is the identity function on AB, and psi compose phi is also identity on 0, 1. That makes you phi is inverse to phi. Psi is inverse to phi. Yeah. Now, how to make negative orientation? For negative orientation, one needs to do this thing, that the interval AB, one needs to flip the interval. That means one needs to get a function which transform A to B and B to A. Once it is done, then you compose with that function, it flips the interval, and hence it flips the orientation too. So example is this function on interval AB, A plus B minus X. So when X is equal to 0, X is equal to 1, it gives the point B, and when X is equal to B, it gives the point A. And in that case, if you compose this function with gamma, where gamma is on in the interval AB, essentially it will be looking like gamma of A plus B minus X. and then it will give you the negatively oriented curve. Why? You look at what happens at x is equal to a, you get gamma of a plus b minus a. That means gamma of b. And at b, one will be getting a plus b minus b. That means a, gamma a. So at point a, one would be getting gamma b. At b, one would be getting gamma a, which is opposite to the previous case, that at a it is gamma a, at b it is gamma b. And this oppositely oriented curve is denoted by minus gamma, sometimes gamma inverse also. Okay, so I think we are running out of time. Maybe I'll skip some of the things. So now we are very quickly going through the way we can measure arc length. So suppose it is the function gamma defined on the interval AB, and we are going to measure the length of this function, length of this curve. So for that one, we'll be subdividing the interval AB into some finite partition, using finite partition, and then we consider accordingly the points on the curve and approximate by straight lines, and you find the length of the straight lines. Take some of the length of the straight lines that will be roughly approximate the length of the curve, and we define if so let us do like this. So if ln denotes this sum where n many points are there here, the sum of the length of the straight line segments, sort of the nth approximation to the length, then this ln actually forms a sequence of real numbers. If this sequence of real numbers is convergent, that means if limit n tends to infinity, ln is a finite number, we call the length of the gamma is existing, and the quantity of the limit is called the length of the gamma. Now the thing is that how to measure it. So one can look at this process, that under the square root, what I've done here, found the length of each of the line segments. So xti yti is the point pi, and xti minus 1 yti minus 1 gives the point pi minus 1. So their distance is nothing but this, and the sum you take and take the limit. What you do, you divide by delta t, and we can take delta t to be the same for each of the partition, okay, sub partition pi minus 1. It will so it will go in under the under root by square, and whenever you take limit, since n tends to infinity is equivalent to saying delta t tends to 0, as number of point increases to infinity, the distance between the points becomes 0, tends to 0. In that case, one can see that we can write under the square root as derivative of the function xt yt. So what was xt yt? Xt yt was the curve gamma. So have I written it here? No. So this gamma, if you are thinking in R2, then it will look like xt yt. So that xt yt we are talking about here. So that we can write if gamma is differentiable. Okay, so it is looking like this. So let me go here and write that gamma t is your xt yt, and whenever we say gamma prime t or ddt of gamma would be the ddt of xt, ddt of yt. So this we can write provided gamma is differentiable. This means each of the component is differentiable. So whatever you have written is possible is gamma is differentiable. That means gamma prime t exists. But once we have this one can check this is nothing but the Riemann sum, and Riemann sum is sort of finite if the function is Riemann integrable, right? So now when we can say that this is Riemann integrable, so we know that if the function is continuous, so if this under square root this function is continuous, then it is Riemann integrable. So what do you mean by the under root function is continuous? So square root function is automatically continuous. This sum is automatically continuous function. Square is automatically continuous function. So what it remains is this derivative. So each of the derivatives should be continuous. Then we can say the function is continuous and the Riemann integration exists, and hence the limit exists. So it eventually means the gamma prime t should exist, and gamma prime t, that means derivative of xt and yt, should also be continuous. So that tells you we need gamma to be C1 type function. So it gives a theory, tells you that if the curve you have taken is C1 type in the closed interval AB, then one can find its length, and the formula is exactly this: integration a to b gamma prime t its norm dt. So that's the theorem. So one can check that if you change the parameter, then also the length, the way we have calculated, is not affected. This is the same. Now what we want is a process. So let me go on the board. We want something like this. We do not want to measure the curve. So this is the curve gamma from interval AB to suppose arc2. This point is gamma A, this point is gamma B, and suppose this is C1 type. So we know in that case length of gamma is existing, and we want a function which will measure from this initial point to any point x, its length. Any point x length here means it will look like gamma x. And the function, when it is evaluated at the point B, it will give you the full length. Okay, so I hope it is clear. So that means whenever I take, so this is a function, this will be a function from the interval to real line, such that s of a would be giving you 0, and the s of b would be giving the full length of the curve gamma. And for intermediate points x, it would be giving only the portion from initial point to that point gamma x, that portion's length. Obviously, if I put it from a to x, then I'll be getting that portion's length, and hence it will define a function. So sx I'll define from a to x, where x is in between a and b somewhere, norm of gamma prime t dt. Then this is a function which will be exactly serving the purpose. Note that this function is a surjective function from the interval AB on the interval 0 to gamma. Why? Because it counts every portion of the curve, no, every finite length, including from the first point to last point. So it has to be an surjective function, from the interval AB to 0 to length of gamma, and it has many properties. Those we'll be learning. One should note very carefully the way this function has been defined completely depends upon this parameterization gamma. So if the parameterization changes, that means the domain changes, the function also changes here, because this function depends upon the domain of the gamma. So since domain of gamma and domain of s is the same, so the function very much depends upon gamma, and hence in that case we should denote by s gamma. Okay, so we will, whenever we'll fix a curve, we will be fixing its parameterization and talk about the function suffix that one. So we'll be discussing some properties of arc-length function. So before that, we define what is a smooth function, smooth curve. So a curve is a parametric curve is called smooth if the tangent at every point is non-zero. And how tangent is calculated? It is the derivative of the curve. So if gamma suppose in R2, then it would be looking like xt yt, xt comma yt. Then the differentiation of the curve will be looking like derivative of x prime t, and derivative of y prime t. So then it means that x prime t and y prime t is never 0 0, never becomes 0 simultaneously. If that is happening, then we say the curve is smooth, provided this is C1 type. So C1 type and tangent non-zero always will be called smooth curve. Next, the property of the arc length function. These are very easy properties. The first property says the function, arc length function, is non-negative. That is very clear because it measures the length of the curve, how it can be negative. And at the point A, it is 0. Of course, it is because it is integration from A to A, norm of gamma prime t dt. So that would be 0, of course. And SB, the full length, because that is how the S function has been defined. Number 2, S is continuous. Number 3, S is differentiable. And number 4, S is C1 type on AB can be proven from the fundamental theorem of integral calculus. So what fundamental theorem of integral calculus says? So it says, it says the following. Suppose you have a function f from the interval AB to R, which is continuous. Suppose continuous. Then integration of f along AB existing, and if you define a function capital Fx by integration a to x ft dt, then it can be seen this is primitive of capital F. So essentially it says that any continuous function defined on an closed interval has a primitive. Now primitive means it is something like this: ddx of fx is fx, and that is happening for all x inside AB. So the function fx is defined for all x in interval AB. So the domain of f and domain of capital F and domain of small f is same. So if you apply this property for the our given case, so in that case your capital Fx would be norm of gamma prime x, and integration from a to x norm of gamma prime x is your Sx. So then S is differentiable by fundamental theorem of integral calculus. And after differentiation, what you get is the function f. That means the function is not only differentiable, so you get ddx of Sx is fx. So not only differentiation, after differentiation you get what is continuous. That means the function S is C1 type. So that's all. So that solves this 2, 3, and 4. Now, if you assume the curve gamma is smooth means gamma prime t is never 0. So gamma prime t is never 0, then S is strictly increasing. So one can say it very easily using picture. So it is like from the interval A to interval B. So at A, you are drawing the curve S. At interval A, it is very much clear that S of A is 0. So here this is your S of A, 0. But at the same time, what is given, Sx from A to x norm of gamma prime t dt, this quantity is always positive. So gamma prime t, we know its norm is always non-zero. But once we say that gamma is smooth, it would tell us that norm of gamma prime t is always positive, strictly positive. And hence, the integration cannot be 0 anywhere except at a to a0, and except it will be counting the proper area. So the curve Sx has to be increasing. So in other words, if you, so this is a curve of S. I mean, sorry, the pictorial description of S. Now, if you want to talk about in terms of this function's pictorial description, so that it will be looking like a to b, and gamma prime t, its norm is always positive. That means it will be looking like this. It is always positive. So then how can the area be 0? Never 0. So it is 0 only at a. Otherwise, at here, at any point x in between AB, you'll be getting always a finite value, which is non-zero. So that's how when gamma is smooth, the function S is strictly increasing. And S is smooth if gamma is smooth. That is obvious, because if gamma is smooth, that means already unit is CN type and its norm is non-zero. So then you'll be getting my previous page where, let me write it again. So by fundamental theorem of calculus, what we get, the ddx of Sx is norm of gamma prime x. So that is happening for all x inside AB. So once you have this is non-zero always, then Sx is also always non-zero, its derivative. That means the function, S function becomes smooth. S function first of all become differentiable. Then it is, since this is continuous, the function S is once differentiable and the derivative is continuous, but the derivative is now non-zero because gamma is we have taken to be smooth, and hence S becomes smooth. So smoothness of gamma ensures the smoothness of S. So with this, we can calculate for some of the curves which you already came across. One is for the circle, and one can check that its derivative is minus sine t cos t, and hence S gamma, if you calculate, it is 0 to x norm of the tangent dt. For sure, one should check before that one that both gamma, this gamma and this delta, because we're talking about gamma first. Gamma is C1 type. C1 type means it is differentiable because each of the components is differentiable. And after that one, you look at each of the component is continuous, so it is C1 type. And hence we can apply this formula. Then one can calculate this norm of this tangent, and it is very much clear that is sine t squared plus cos t squared is under root, which is 1. And hence for this gamma, parameterization gamma for the circle, the arc length function will be x. So clearly at t is equal to 0, it is 0. T is equal to 2 pi, and we know the perimeter of curve or length of the circle. Here we should talk about length of the circle is 2 pi. Next is if you take the different parameterization here, cos 2 pi t, sin 2 pi t, where t is running between 0 to 1, then one can calculate. Okay, so I'll take maybe 5 more minutes. Is it okay? Then one can check that the function changes. It becomes 2 pi x. However, at 0 you'll be getting 0. At 1 it is 2. So here the thing is that in both cases we see the function, the arc length function depend upon the parameterization fully. And one case is something that its differentiation becomes 1. I can give one more example where I can take the part of x-axis from a0 to b0, and parameterized in this fashion: a plus t comma 0, where t is running between 0 to b minus a. So it is a line segment from a0 to b0, and one can check the arc length function is 1. Sorry, arc length function is x. So in two cases we have seen, here it is arc length function is x, that means derivative is 1. Here also arc length function is x, that means derivative is 1. So the derivative 1 arc length function has is quite important. So let me go directly towards that one. So what derivative of arc length function is about? I mean, it is something, it tells us the rate of change of or rate of measurement of the length of the curve. Obviously, both Sx and differentiation of Sx depends upon the parameters, and as parametrization changes, those are changing. And if we talk about a process or method for which the differentiation of that arc length function is always 1, note that by fundamental theorem of integral calculus, it is norm of gamma prime t, norm of gamma prime x. It is always on 1. Then see, it is always 1 for any curve. So it is, I'm talking about, is there any parameterization for which the differentiation of arc length function is always 1? In a sense, the arc length function is always x, or translates of x. It will look like x minus a is constant. Then it will tell you that the process is sort of a universal or uniform. So parameterization process is uniform in some sense, that will come to. It also tells you a feeling that suppose you have two lines. One is, so it is something like this. You have one line, straight line segment. Suppose it is a0 to 0b, sorry, b0 is coming from the interval a to b on the axis, and you bend this this straight line segment. So after bending, it will look like possibly like this, possibly like this. So, and I told you bending means each and every point is sort of given a weightage. So you have given a weightage, it has been bended. It has been bended, but the length has to be same. So here the length was b minus a. After this change, so change has been given, change has come through some weightage. Here also the length has to be b minus a, but that is not very much clear, because this parameterization process is something that where this ddx of sx is not 1. If it is 1, it will make sure that even if you bend it, then the stretching is not happening, and the length of the curve is same. So also it will be looking at like this, that if a particle is moving on both the curve here and here with constant speed, then it will take same time to reach from the last point to first point. So from here to here in both the curves. But that is not evident the way we parameterize. So if parameterization changes, that means the vector changes on that one. And if the vector is representing the position of the particle, the differentiation is different. So in that case, the tangent changes, that means speed changes. So we don't want that one. We want the speed to be same here and here. Why? Because we want how the particle is changing the direction. That is the thing we want to observe. It is something related to the count of the count of curvature. Curvature will depend upon that how the direction is changing. So rate of change of the direction. So it is like if particle is moving constant speed in both places, how the rate of change is direction is happening here. I mean, how is changing its direction here compared to this most simple case. So we need a special parameterization for which this rate of change has to be constant. So what should be the special parameterization? So it is here. I'll skip some of the things. Yeah, so we need a special parameterization, and how it look like in that case, whenever through that parameterization one calculates length of the curve. Length of the curve is from a to b gamma prime dt. But if the parameter you change correctly, so that it feels that you are on the curve, it has been bended, the straight line has been bended to become the curve. So the first point and last point will tell you the full length. So that means it is starting from 0, because here the length was 0, full length is L. Here also it is the same. Here it is also 0, full length L. But previously it was A, B, gamma B, but the length was not counted like that. Okay, so that depends upon parameters. And so we are asking whether any parameterization is given such that here the parameter also runs between 0 to the full length L, and here also accordingly the length will be getting. So here the parameters will learn from 0 to L. If it is 0 to L, then question is what this du? Because yeah, so I'll come to that one. What should be du? So maybe one can guess from here that if you want to have a du here, then this you cannot kill roughly. So this thing you have to replace by u. So u has to be this function. And one can guess that this possibly one can write as ds gamma. So the guess is this u is nothing but the function coming from s. That means u is related to this s itself. So and here in that case it will be from 0 to from 0 to L. So in that case what we want, a function from 0 to L to AB, which will be converting the interval 0L to AB, strictly increasing surjective C1 type, and smoothness should be preserved if the gamma is smooth, so that the property of the gamma is not changed at all, and the orientation of the gamma is not changed at all. That's all. And what is our aim? Aim is to make the differentiation of S to be 1 here. And what is differentiation of S? The norm of gamma. Now norm of gamma we cannot directly change to 1, but I can change the parameterization where I can have something, a factor 1 by gamma here, its norm, so that it will cancel, and hence we'll be getting 1 here. So that's the idea. So the function, if theta is the function, its derivative has to be 1 by gamma prime. So question is that is there any function? Answer is yes, there is. This S gamma itself will do it. What was S gamma? S gamma was function from AB to 0 to L. What about its inverse? So question is the inverse existing? Answer is yes, that also true. So here are the properties of S gamma we have noticed. If gamma is smooth function, C1 type as and tangent is non-zero, then it is non-zero function, strictly increasing, continuous, differentiable. It is C1 type, and S gamma is smooth if gamma is smooth. And hence it can be seen that S gamma inverse also satisfies all the property. Not only it is existing, it also satisfies all the properties. Because S gamma is strictly increasing and surjective, S gamma inverse exists. Continuity of S gamma inverse is confirmed by the bijectivity of S gamma function, which is defined in the compact interval, and differentiability is also ensured by the differentiability of S gamma. And derivative of S gamma inverse is exactly 1 by the gamma prime x, its norm. So the answer is very simple. you you convert the interval AB to interval 0 to S gamma, sorry, 0 to gamma, length of gamma by S gamma function, and compose. So once we compose, the new gamma, we say, has a parameter S. S denotes this function. This function's what is called parameter. The parameter is running from 0 to L. And you have everything now. So we have achieved, so we are not talking about, because time is already over, we are not talking about this curvature again. Let us skip it for the time being. So let us stick to up to this much. Okay, so we have got one parameterization which is sort of universal in nature and gives you a feeling. Previously you had your one curve which is straight line with a given length L, starting from 0 ending at L. That's why it is length L. Now you have bended with some weight, and the process of parameterization does not change the length. It remains the same. And that parameterization is nothing but this parameterization. Since this parameterization is coming from the arc length function, we call it is arc length parameterization. Okay, so with this I'll stop. I have taken, I think, 10 minutes or more extra. I'm sorry for that one, but okay, I hope it's useful to you. Thank you. Yeah, I'll be very happy if you ask questions, because I'm sure lots of doubts will be there, because in a short span of time I have covered many things. And if students are there, they should, I'll be telling you, telling the students to go through the material. I'll be sending the material for sure. Go through, and if you have any question, you ask me later also. And even now, if you can, I'll be very happy. Mhm. Thank you. Yeah, actually, whatever we could not learn, we try to deliver them. Mm. Thank you.